What we started talking about last time was proving what the language of the DFA is. I didn't ask you to do that, although, you know, on the quiz for next time, perhaps I could ask you to prove that actually these things are accepted on this DFA. Informally speaking, I hope that everybody can see how, you know, you do a bunch of B's and then an A, but that's not a proof, right? That's what we are talking about today. How do you actually prove such things? And like I said last time, these proofs always use induction. And I wanted to do a simple example. So I have 2, and then I got 1 for you all to try, and that'll probably do it for today, but I got more, you know, more where that came from too. Anyway, here is a very simple DFA. I'm going to give names to the states because I want to write down, you know, you're going to have to write down details about the transition function, delta, and therefore you need names for the states so you can write down what you want. All right, and what I would like to do is let's prove that this accepts all strings of the form, well, the alphabet is just A's, and this one accepts all strings which have an even number of A's. The best way to write that is that, A to the 2n, right? This means an even number. You could say A to the n where n is even, but that's less convenient. It's more convenient to write it this way, A to the 2n, all right? I want to prove that this accepts all strings of the form A to the 2n. Now, first of all, we should try to write, even that is a little bit less formal than I would like. So I want to write this formally in terms of what it means for a string to be accepted. And we said this towards the end last time. What it means for a string to be accepted, was it towards the end? I think it was towards the beginning last time. Whatever, it doesn't matter. It means when you start in the starting state and you do this string, you end up in the accepting state, which here is x. And the way to write that, formally speaking, and this looks kind of crazy, but once you get comfortable with all of the notations and whatever, I hope that this will seem all right. So what that says is this x here represents the starting state. And what this means is if I start in the starting state and I read through this whole string, a to the 2n, the state I end up in is x, which is accepting. So this is the accepting state. Now in this example, the starting state happens to be the same as the accepting state. That's not always the case, of course, but here I'm using x in both of those places. In a different example, you might use different things here depending on what's the starting state and what's the accepting state. All right, this is what needs to be proved, and this, my friends, we prove by induction, where this n is the variable that you do the induction with. All right, this will look different from those. You know, we were doing sort of practice induction proofs last time with just adding numbers together or whatever. This is totally different from that, but the structure of the induction is the same. You begin with the base case, which is when you do the case when n equals 0, and then you do the induction case. And I'm realizing at this point, there's going to be a key step later on where we use, this is a reminder from last time. Can I just squeeze it in here? I meant to say this at the very beginning. This is the sort of important property of the delta function. Property of delta star. It was this somewhat weird looking thing, and we talked about this at length last time. This means if I start in some state S and I read the string x followed by the string y, what is that? It means the same as this. And this formula, you know, I might say memorize that, or more likely you're going to do so many of these examples that you'll just remember it naturally, but that is super important, and this formula represents sort of the key step in every proof that you're ever going to write about DFAs. So this is, you know, very weird looking and kind of confusing, but I hope that everybody can remember that, or at least write it in a safe place. Get that on a tat. Put that on your bicep. really turned some heads there in the club. All right. Okay, anyway, that's a little, we are going to use that formula in the box. But let's do this. So I'm going to prove this by induction on n. All right. We begin with the base case. Now the practice inductions we did last time, the base case was n equals 1 because we were proving formulas that didn't make any sense for 0. But in this, pretty much always in this class, we're always going to use n equals 0 as the base case because this n refers to any natural number including 0. So the base case is n equals 0. Let's say what do I have to show here? We have to show, maybe I'll put, the thing that we're trying to prove is this thing in the green box. So I have to show that that is true using n equals 0. This will say delta star x a to the 0 equals x. All right? This is what we must show. Okay, how do we show it? So the base case, as usual, is pretty much always easy. It's usually once you write what you want to show, you end up with something which is obviously true. Maybe if I had to write some steps, I might say this. A to the power 0 means the empty string, right? It's a string consisting of 0 a's. And what is delta star of x in the empty string? It means if you start in state x and you do the empty string, which is nothing, where do you end up? The answer is state x. I don't know what's up with this screen.
It does it in other classes too.
Oh, yeah? In this room or in other rooms? This room. All right. Just got to wait a few seconds. Sorry. All right. Anyway, this is what we wanted to show, right? This thing is x. So base case pretty much is always going to be easy. All right, let's do the induction case. That's the more interesting one. Okay, so for the induction, I write down the induction hypothesis first. So I'm going to say assume. I write the thing in the green box, but using a k. Delta star of x a to the 2k equals x. This is my induction hypothesis. And then what I want to show is that same thing but using k plus 1. X a to the 2. Make sure you put these parentheses in the correct spot like I did. All you parentheses haters out there, it's not a good look in the club to be a parentheses hater. I know it. All right. It's important because 2 times k plus 1 together is still even, right? If you don't put the parentheses there, it would be odd, which is not even true in this example. That's what I want to show. Okay, let's do it. This is just a little throwaway words, this little proofwriting style, just to separate out what I'm assuming, what I want to show from what I'm actually showing. Here's the real meat of the proof. So start with, what I want to show. I start with the thing on the left-hand side, simplify a bunch of times, hopefully ending up with x. A to the power 2 times k plus 1. Anyone want to suggest a way to simplify? You don't need any kind of big idea. There's one thing that seems to me to be an obvious thing I would like to simplify. Yeah? Distribute to 2, yeah. I don't know what's going to happen after that, but if you've been raised right, you should feel like, yeah, maybe I should distribute that too. So it's 2k plus 2 now, all right? Now you have to have some little bit of an idea, I suppose. And as we do more and more examples, I think you'll see sort of how these things usually go. I'm going to write, instead of 2k plus 2 up there, I'm going to kind of split off a to the 2k followed by a squared. All right? Of course, a to the 2k plus 2 means a itself over and over again, 2k plus 2 times. But this is the same as 2k times and then another 2 times. And why did I do that? It's because what you see like right here, just that part, is what I have in the induction hypothesis, x comma a to the 2k. So I like to see x comma a to the 2k. Now I have this extra thing over here, which we'll have to deal with, but I like to see x comma a to the 2k because that's my induction hypothesis. How do we deal with this extra thing? Well, this is where we use the thing I wrote in red up in the corner. This is how you handle delta star of a thing followed by another thing. When the string is split into two parts, you do this to it. So you have to, read that formula carefully and make sure you get it all right, but it's going to say delta star of delta star x a to the 2k, comma, a squared, like that. So this is that rule about delta star of one string followed by another. All right? And now I feel very good indeed about this part right here. This is exactly what appears in the induction hypothesis, which I scrolled a little bit, but you can see right there. This part, delta star of x comma a to the 2k equals x by the induction hypothesis. So I can say this equals, and this is the step in which I use the induction hypothesis, x right there. All right? And we are pretty much done at this point. What is delta star of x and a squared? That just means if you start in x and you do a, where does it end up? And for that, you can just look at the diagram. What is it? Delta star of x and a squared. Right here, if I'm in x and I go a, the answer is x. All right, so right here, I say x, the end. Remember, what I was trying to show is that this delta star of x comma 2 to the a to the 2k plus 1 is x. And that's what I started with. I ended up with x. So it all worked out nicely. Anybody got questions about that? Let's try another one. And then I got one for you all to try. Let's try. This is actually almost the same as the one that was on the quiz. Sorry, this doesn't make sense. That's supposed to be an A up top. All right. This time I'm going to call the states STU, just for fun. Like so. All right, so I would like to, let's first of all say what kinds of strings are accepted, and then let's try and prove it. Can somebody say what's a formula for the strings which are accepted? This accepts, what do you think? Yeah? A to the NB, yeah. This is almost exactly the one on the quiz, isn't it? Very similar. I think the quiz just had A's and B's reversed in that position. All right? So let's try to prove it. Prove it accepts A to the NB. All right, so maybe we should recall, if you can glance back at the other proof, we're going to follow very much the same structure. The first thing that you should do is write, formally speaking, what you're going to try to show. And this is some kind of statement involving delta star of something equals something, right? Anybody think you can fill in the blanks here? What exactly do we have to say about this delta star of something? We always should see a state. So what goes here is a state, a string, and a state. What do you think? Someone I haven't heard from, maybe? What do you say?
Is it S, A to the N, B equals T?
Yeah, I like that. Yeah, excellent. Delta star of S, A to the NB equals T. So this always, the format of this always goes, this is the starting state, right? This is the string which you're trying to show is accepted, and then this is the accepting state. Right? This is always how this goes. So you should always be able to kind of put the pieces together. And that is what we are going to prove by induction on N. Right? So let's do it. The individual steps should be hopefully, similar to last time. So I'm going to prove this by induction on N. All right, we start with the base case, which is N equals 0. So what I want to show is that delta star S A to the 0 B equals T. And if you just write down what that means, it should be immediately obvious. This says delta star of S, and A to the 0 B is just the same as B, right? Because A to the 0 is like nothing, the empty string. And what is delta star of SB on the picture? That just means if I start in state S and I do B, it equals T. So the answer is T. Check. All right, the base case is hewn. All right, and then the induction case. This is the more interesting part, as always. I'm going to say assume that delta star S A to the K B is T, right? I'm writing that thing in the green box, again with a K. And then we have to prove that same thing, but with a K plus 1. So I want to show delta star S A to the K plus 1 B equals T. All right. And let's do it. I start with the left side of what I want to show, delta star S A to the K plus 1 and B, all right? Sorry, my S looks kind of like a delta. That's a S, not a delta. A little too curvaceous on the bottom there. Right? What should we do from this? You know, last time, at this point of the proof, it involved sort of separating things out. I had A to the 2K plus 2, and I wrote that as A to the 2K separately times A squared. Now here, I see A to the K plus 1 and B. Look at the induction hypothesis. The induction hypothesis involves A to the K and B. So I want to rewrite this in such a way that it has A to the K next to a B. Can anybody see how to? So I'm just going to re-express that string. But I want to do it in a way so that there's a to the K is next to a B. Yeah?
Do it A and A to the K.
I like that. A to the KB, right? And the purpose of doing that is so that I have A to the K and B together, because that will match this up here. And next we use that fancy rule with the deltas. So here, thinking of this string as, you know, like this one followed by that one, right? It's A first and then A to the KB. So my fancy delta property, I don't really have a name for that property, but it's this. SA and then A to the KB, right? Break up the string. And now can we simplify this? The innermost thing is delta star of S and A. And what is that? Well, that's just, if you start in S, where does the A arrow go? That you can see on the diagram is S, right? So that is just S followed by A to the KB. And what is delta star of S and A to the KB? That's the induction hypothesis. It is T. So this is my very last step. The induction hypothesis says T, and that's it. That's how we do it. Any questions or thoughts about that? All right, I got one for you all to try. See how you like it. This will be pretty similar to those other ones. All right, so in this case, I didn't give them names, but you know, just to draw the DFA, you don't have to give them names. But when you write the proof, you're going to need to give them names. So you can give them your own names. But your job is to find which strings are accepted, and then prove it. It should go like the ones that we just did. See what you think. I'm going to write my answer up here. Everybody seems to be doing great. All right, can we talk about these? It looked like folks were doing great. So first of all, you have to state formally what you're going to show, which everybody ended up saying something like this. I used S and T for the names of those two states. Actually, I called this U, but you never have to mention U in order to prove this. The base case, as usual, is simple. A times B to the 0 is the same as A, and then delta star of S and A is just, looking at the picture, you can tell this is T. And then for the induction, we assume A B to the K goes to T, and we have to show that A B to the K plus 1 goes to T. And we start with the K plus 1 here. Split that apart as A B to the K followed by B, because I want to see A B to the K together because that's the induction hypothesis. And then do your favorite property of delta here, S A B to the K comma B, like so. Then the induction hypothesis means that first big delta, or the inner delta equals T, comma B. And then what is delta of T, comma B? You again look at the diagram. Starting at T, you do B. It goes back to T. So this is T, as desired. Right? Any thoughts about that one? I hope that it worked out for you. It certainly looks like a whole bunch of fancy nonsense, but I hope it makes sense from step to step. All right? Great. We got 10 minutes left. These ones that we've done so far are kind of easy ones, so I want to do ones that are slightly more complicated, and they can be complicated in two ways, and maybe we'll at least start talking about the first way in which these can be a little bit more complicated. So here is one which really doesn't look very different at all. I'll tell you what's going to happen. Sometimes you need a lemma. Lemma is a fancy mathematical word for like a sort of like a helper theorem. When you call something a theorem, that's like important. When you call something a lemma, it's like, yeah, it's cool, but it's mostly a lemma is used in order to prove a theorem. But it's still like a true thing which you write the proof of. Anyway, you'll see what I mean here. This is different. It doesn't even look all that much more complicated, but it's different in a very specific way, which makes the induction not work if you just try to do the induction like we have been doing. All right, and X is the starting state. So let's try to do the same thing, and I'll try to indicate like why the typical approach that we've been doing doesn't quite work. First of all, can anybody say what are the accepted strings in this case? Can we say what they look like? Think about what does it take in order for you to arrive at Z? Yeah? A, B to the N, A. Yeah, I like that. A, B to the N, A. Right? Okay. You got to do one A to get here, then some B's if you want, and then one more A to get to the acceptance state, and then nothing else, because if you do something else, you go down here. Sorry, I meant for this W to be a... It has to have that, or else it didn't have any outgoing arrows before. Okay, A, B to the N, A. Now, let me give you, I don't know if you want to write this down, because this is explaining why the standard approach will not work here. Think about the induction step here. If I was to just do the same thing The base case is still easy to do, but the induction, maybe I'll just write this more formally first of all. What we have to show is delta star of x, a, b to the n, a equals z, right? X is the starting state, z is the accepting state. Okay, what's wrong with that? That's not wrong, but it's going to go wrong if you try to prove it in the same way as we always do. In the induction step, you would say, assume delta star of x, a, b to the k, a is z. And then I want to show delta star of x, a, b to the k plus 1, a equals z, all right? And the problem with this is the standard approach that we have always been doing before would be you want to write this as a, b to the k, a times something. That's how we have always done it, because ab to the ka is the thing which appears in the induction hypothesis. And so I would write that as ab to the ka followed by some other stuff, or maybe with some other stuff in front of it. This is exactly how it went, say, in this one we just did. I had ab to the k plus 1. I wrote it as ab to the k followed by b because I wanted to see ab to the k because that's what's in the induction hypothesis. But that is not possible here. You cannot rewrite ab to the k plus 1a as ab to the ka followed by something else. It just ain't true, right? It's because here really the issue is ab to the k plus 1a doesn't have ab to the ka as a substring, right? And so you cannot break it into those two bits, which means you don't have anything to use the induction hypothesis with. That's the problem, all right? The problem, if you think like very specifically about this, is the issue is the k was in the middle, not on the end. If you think about like why this didn't work when the other examples did work, it's because the k was in the middle and not on the end. That's really the root issue why at least the same strategy did not work, okay? And so the solution to this issue is we prove a lemma about what happens when the k really is on the end. All right, so, and this can be a little tricky. You have to be able to look at this, realize that you actually cannot prove this as is, and then figure out what else should I be proving. Really, instead of a, b to the n, a, I want to prove something about just a, b to the n. Okay, so in this particular example, I'm going to write a lemma. This is something that I'm going to prove using induction. This is not actually the big thing I want to prove. It's just a little piece of what I want to show. But what I'm going to show is this. Delta star of x, a, b to the n equals y. All right? So this is only part of it, but it says in my diagram, what you eventually want to prove is about how to get from x all the way to z. But that's not possible to do directly by induction. But instead, I'm going to prove what happens when I do a, b to the n. It ends me up at y, all right? That's sort of halfway there. And then you do the last step separately. The last step is actually much easier because it's just a single a. But anyway, this is what I want to do. Prove this lemma. This we can prove by induction in the same old way that we always have. So I'm going to prove this by induction. All right. Can I, just because we have to leave in 3 minutes, I'm going to kind of abbreviate this if you don't mind. Base case, easy. That's my abbreviation. The induction hypothesis, or the induction case, I say assume delta star x a b to the k equals y. And then I want to show delta star x a b to the k minus 1 equals y. And the way to show it is just like all the other examples we've done so far. I write, instead of a b to the k plus 1, I write a b to the k followed by b. And then we split that up into deltas. Delta star x, comma, a b to the k, comma, b. That first part is y, so this says delta star y, b. And on the diagram, you can see that is b, because y has an arrow back to itself. All right, so the lemma is proved. All right, so now we know, we have shown delta star of x a b to the n equals y. All right? That was the lemma. Sorry, I did that kind of quickly, but all the details are exactly the same as those other examples that we have just been doing several times. All right? How do we actually finish the real thing that we are really trying to prove? So I'm going to write this as a theorem. This is like the real deal. So usually a lemma is something which is kind of like a helper, or it's not really what you want to talk about, but you have to prove it in order to prove something else. The real deal is, of course, this, right? This is the original, the actual statement that we're trying to prove about this DFA that tells you what strings are accepted, a, b to the n, a. But now that we've proved the lemma, this is very easy. So I go delta star, I don't even need to write any words. I'm going to split up the string a, b to the n, a. The lemma already tells me about how to handle a, b to the n. So I'm going to split up the string as a, b to the n followed by a. And I get delta star x, a, b to the n, comma, a, right? And then by the lemma, the first part is y. This equals delta star y, a. That's by the lemma. And then what is delta star y, a? That's just, look on the diagram. From y, the a arrow goes to z. So this equals z. And that's what we wanted to show. All right? So it's a bit of a journey, and from the point of view, I mean, I hope that every individual step makes sense, but maybe the hard part is just deciding. You look at this, you have to decide for yourself what the lemma is going to say. The lemma is going to say you only go here to y first. Prove that by induction, and then do the last step. We're going to do a couple more like this next time. All right, I hope you all have a good weekend. Look out for the next homework assignment. I'm going to go and post it within the next hour or so. Due on Wednesday, as always.